Can folks see
You
that?
can see it? Yep, perfect.
Great.
Thank you.
Hi, yes. I'm Quinn Thomas. I'm an associate professor at Virginia Tech and the lead of the uh, Ecological Forecast Initiative Research Coordination Network, which is a U.S. National Science Foundation funded project to kind of galvanize the ecological forecasting community around forecasting data from the National Ecological Observatory Network. The RCN, as we call it, is a component of the larger ecological forecasting initiative, and kind of represents the Neon Ecological Forecasting Challenge as the central tool for collaboration within the Research Coordination Network. So I'll get started. So, one of our big goals is to make more intercomparable forecasts from a diversity of perspectives and approaches that engages more partners. And so that involves getting a lot of folks involved in ecological forecasting. And so we saw this opportunity when the National Science Foundation kind of put out a call for these research coordination networks centered around NEON data. This was back in 2019, to really kind of bring together these two kind of activities, which is the Ecological Forecast Initiative, which is a large grassroots consortium aimed at building the community of practice around ecological forecasting. Where Mike Dietz is the head of the steering committee for that, and helped really launch that off the ground. The other is NEON, and NEON is an NSF-funded effort run by largely run by NSF, and it's standardized terrestrial and water data, freshwater ecosystem data with ongoing collection that is freely available across 81 sites across the U.S. And it's funded to continue for a 30-year horizon in the future. And so we created this project to use NEON data to kind of build the community of practice in forecasting. And we're really, first, I want to acknowledge the current steering committee that's behind this project, particularly Jody Peters, who's the program manager and has been really kind of instrumental in keeping all the bits going forward. And Carl Bodeger has done a huge lift on the cyber infrastructure behind the scenes as well. And we, when we came together and asked ourselves, like, how can we get folks really kind of excited about forecasting, we're really kind of inspired by data science competitions that were occurring, and they're increasingly kind of occurring in the environmental space. And so that sort of got us fired up about this idea of designing a challenge to have folks try to predict NEON data before it's collected. And these are just some examples of other work out there that's sort of in this realm of a data science competition or a forecasting competition. And so we created the NEON Ecological Forecasting Challenge, which you can read about in this publication here. We view it as a platform that challenges and empowers a community to submit iterative near-term forecasts of yet to be collected NEON data. And there are a couple of important terms in here. A platform means that it's kind of built on top of the NEON program, and there's many ways for folks to use it. You'll see, I'll talk about using it in classes, or you can kind of like, you don't have to go after all variables at all sites. You can choose how to use it. It's a platform that tries to empower folks. It's iterative near term, meaning that the challenges are asking you to make forecasts of day to 1 year ahead at most. And it's iterative because it accepts forecasts all the time. You can update your forecast in a week ahead tomorrow. We'll just get closer to the date that you're actually trying to predict, but you can still update it iteratively. And then yet to be collected means that it's a genuine forecasting challenge. What's great about that is the organizers can be part of it because there's no holding back data. And so no one knows the future data to be collected yet, so we can all participate. And so here's the underlying kind of processes that underpin the forecasting challenge and the components that we sort of see as important. It starts with an ecological observatory network, which in this case is NEON, but could be a single PI's buoy in a lake. It doesn't have to be a gigantic, federally funded research effort to run a forecasting challenge around a data stream. But that observatory network, let's see, and I just want to plug NEON again. Here's where the sites are distributed, and it really there's a ton of data products out there. Definitely worth exploring if you haven't looked into the NEON project. And why we're really excited about it is it allows us to ask questions about how predictability differs across ecosystem types, or the physical, chemical, biological components of ecosystems, and also thinking about population, community, and ecosystem scale. And forecasting is really in NEON's original mission, but not part of their current implementation because they're really focusing on the monitoring. And so this effort is really helping NEON meet its mission of understanding and forecasting ecosystems. So the NEON data is then processed into targets data, and the process of going into the targets data is getting the community together and asking, what exactly do we want to predict? Maybe first the community may say, hey, we want to do water temperature, and then but it's like, do you want to do? I mean, it's collected at multiple depths every 10 minutes. And so do you really want to forecast that? Or do you want to forecast the daily mean at a certain depth? How is a community going to handle missing data? Like, do you throw out any day that has some missing data? Things like that involve a community coming together and deciding how to create the targets that are ultimately, the targets are always made available in real time, so you can use it to update and train your model off the latest data, and those targets are then used to ultimately evaluate the model. And as I said, this was really community designed. Back in 2020, folks came together for a virtual meeting and really highlighted the themes that they wanted and some components that they were excited about is natural climate solutions, water quality, biodiversity conservation, infectious disease. And you can really see that show up in the 5 themes that we have that are involve water quality, at the 1 to 35 day ahead, tick larval abundance, the kind of the disease focus there and the populations, water and carbon fluxes from eddy covariance towers. That's really the natural climate solutions. Beetle community richness is a biodiversity aspect, and phenology is another kind of ecosystem level process that was very got a lot of interest. You can see that in many cases we have access to the data within a day or two of it being collected. And so that community design led to these working groups, around the design of the themes, the cyber infrastructure, standards, which Mike led to kind of make it so it's interoperable across these different themes, the forecast submission formats, and partnerships, which led to a 2021 launch. And just here's an example of targets, which are these automated updating time series for training and evaluation. This is all the targets for a Florida site. And you can see it's kind of cool to see all these different ecosystem, or ecological scales represented here. So next, we thought that folks would really want to use weather forecasts as inputs. They don't have to, but they could. And the process of getting access to like weather forecasts for individual NEON sites is non-trivial. And so we wanted to lower the barrier of entry by making that available to folks. And so we download and process NOAA weather forecasts from the Weather Service, the U.S. Weather Service, to download their 35-day ensemble product, which inherently has uncertainty included in it, and make those available for all the NEON sites, where the user can just use some example code we provide to pull it locally to where they're running their forecast. They don't have to work with the gigantic data sets that NOAA is making available that cover the entire globe. And here's an example of air temperature with uncertainty for a single site on a single forecast start date. And so then we have training and templates because to help folks learn how to forecast. And so, for example, we go to meetings and provide training in this. At the Global Lakes Ecological Observatory Network annual meeting, Freya Olson gave a nice talk or a workshop where on Sunday or Monday they learned how to submit to the challenge. They actually did submissions, and because of the low latency, the data availability, they were able to evaluate the first few days of their forecasts by the end of the week. And for fun, she handed out a hat to whoever had the lowest score, and it got really people excited. And many of the forecasts that were generated during that workshop are still being submitted to the forecasting challenge every day. And we also have one at the Ecological Society of America meeting coming up. It's been part of 11 university courses. It's an awesome project where students kind of learn about forecasting over the course of a semester or workshops like this, and particularly in courses, you can really start to see your forecast get evaluated and start to think about how you can revise your models and make them better, which is really awesome. We have a bunch of templates and tutorial code on GitHub, which you can use as basis, particularly for automation the automated submission. We give examples on how to do that using GitHub Actions. And finally, we've thought about broadening participation. And Alyssa Wilson wrote a nice paper in Ecology and Evolution that addresses this. So now forecasting teams submit their forecasts. They take the targets and numerical weather forecasts or anything else they want to generate a forecast, and they submit it to the forecasting catalog. And as of kind of last update was about a month ago, we've had over 200 teams submit nearly 14,000 forecasts. That a large part of them are a combination of submissions to the phenology and aquatics team. On the left is the number of teams, and since it's an iterative thing, teams have submitted multiple forecasts. And the right is the total number of forecasts for that theme across the different teams. And so you can see that the aquatics and phenology and terrestrial have gotten the most submissions. Those are actually the ones that had the lowest latency. We think those are connected. And so actually at a RCN meeting in in June, a group got together to really think about how to grow the beetles theme in particular, and what are some of the barriers of entry there. So we also want to ultimately compare forecasts to a set of logical kind of baselines. And so for every variable at every site, for every theme, we generate two simple baselines: climatology, which is the historical day of year average for that particular data point with the mean and standard deviation from the historical data. And then the other is a persistence random walk that assumes that tomorrow is the same as today with some uncertainty added. And so those two baselines are generated kind of in-house, so they're made available as a comparative model for folks. And so we also automatically score submissions every day. So we're updating this database of scores, which are the evaluations of the forecasts. And that really leverages the work on these the standardized formats, so that the targets have a predictable format, the forecasts have a predictable format that then can be brought together to generate scores. And the particular score that we focus on is the continuous rank probability score. And the reason we choose that is because a fundamental principle of the forecasting challenge is that forecasts need to have uncertainty. You could submit a single line. It's not going to score well unless you're dead on every single observation. And so we score, our metric really emphasizes robust estimation of uncertainty. And for folks who aren't familiar with the continuous rank probability score, I won't get into like the formulation, but it can be thought about generally like this. So imagine here's your forecast, where you forecast a mean, and you also forecast a standard deviation. If your forecast is 8, and the ultimately observed value is 8, which is this red line, then you see how your score would actually get worse as your uncertainty spreads, because these isolines are your ultimate score, the value the scoring value you get for a forecasted mean of 8 and a standard deviation of 2, or let's say 4 is right here and gets a score of 1. But now imagine that you're not as accurate. You can actually score the same score along this isoline by being less accurate, but actually having lower standard deviation, lower uncertainty, because you're not saying it's between here and here. You're saying it's between a smaller kind of distribution, but it still includes the observation. And so there's this trade-off between being, in the grand scheme of things, you don't get a good score because you say the mean is 8, but the plus or minus infinity. Like that shouldn't get a good score. And so you really want to kind of appropriately tighten your estimation of uncertainty. And so the continuous rank probability score kind of highlights that. And then we make everything available on a dashboard. And so, we're really pushing this forward right now, is this idea of real-time analysis of submissions. What are the high-level questions that folks have that can be immediately answered iteratively every single day that kind of updates as new submissions come in? And finally, kind of, pushing towards synthesis for theory. And on this diagram, the solid lines are the automated processes, and the dotted lines are the non-automated ones that really involve the kind of the community to come together and think about. And we're building up towards a synthetic analysis that really leverages the fact that we have different ecological systems, sites, different times of year that forecasts are submitted, different modeling approaches, and different days of the future or horizon. And there's 2 focal challenge themes that have really started this process of synthesis. And I won't get into the results here because this is only 20 minutes, but I want to point you to the papers that really are starting to think about this. One is by Catherine Wheeler. The preprints available here. It's about the it's the spring phenology forecasting challenge. And you can sort of see how this kind of first cut at analyzing a forecasting challenge is here. The second is this paper on near-term forecasts of neon lakes as a way to think about kind of how to analyze different forecasts that are submitted across lakes. And then this set the groundwork for a synthesis that Freya Olsen is leading right now in the same area in terms of the aquatics, where a lot of teams here. You can see over 50 teams on the right here. These are different team names, are submitting forecasts very regularly. This is the number of forecasts per month, so it's getting close. They're submitting very regularly every day, and is building this database up to do a similar analysis as to what Catherine did for the phenology. And then Abby Lewis and others on the theory working group within FE are kind of submitting a lot of different models, or the same model, to all the themes to kind of understand how transferability of modeling frameworks across different ecological systems and scales. And so, one of the big things we're learning early is that the historical averages and statistics of the data are very hard to beat. And we're starting to kind of think about, what aspects it's easier or harder to beat. And, water temperature, you can do a little bit better kind of beating climatology than phenology is, kind of an early synthesis that's coming out. And so all together, this is a neon forecasting challenge. And, we're really kind of excited about this being a template for others. Folks in the Canadian Ecological Forecasting Initiative are kind of thinking about forecasting challenges using data in Canada. The Terrestrial Ecological Observatory Network in Australia is excited about this. Folks like the USGS and others kind of view this as a way to engage users of data in a predictive way. And this underpinning framework is extensible and reusable for those groups. And so I want to thank you for the opportunity to talk about the NEON Ecological Forecasting Challenge. And, again, ways to get involved: join EFI, submit forecasts. And if you're teaching classes, or, it's awesome that you're using this data in this workshop. And, if you're teaching classes, it's a really great way to use in a class. So all these things, definitely reach out and ask questions about things like that. So I appreciate the opportunity to talk. And if there's time for questions, I'm happy to answer.